This is Lab 2, covering the motion of a falling object. In this lab, we will be covering an object falling from rest. This object will have two forces that we will be examining. The first is gravitational force. Gravitational force, represented by the variable w, is a vector in the direction of negative j, or in the 2D world, negative y. Gravitational force equals mass times the gravitational acceleration constant, which on Earth is 9.8 meters per second. The second force we'll be covering is drag force, covered by force drag. Drag force is in the opposite direction of motion and is equal to the coefficient of drag times the speed squared. Here you can see the video, having been analyzed in Tracker. As you can see, the object, starting from rest, is released and accelerates downwards. When modeling this lab, we had to cover the initial conditions. The first condition is the mass of the object being dropped, which came out to around 0.75 kilograms. The initial object position given by Tracker was 0, negative 0.008, 0, with an initial velocity of 0 as the object started from rest. J hat, will be representing the y plus direction, or 0, 1, 0. Two codes had to be written. The first one using only the force of gravity. As you can see here, the force of gravity equation has been put into this code, with W equaling the gravitational force, and it equals the negative mass of the object times G times J hat. F net is only equal to gravity, the force of gravity. Down here, F net is used to find the ball velocity and then the ball position. The second code that had to be written used both the force of drag and the force of gravity. As you can see here, we have the gravitational force equation and we have the drag force equation, which is B times the magnitude squared of the object velocity times J hat, and F net equaling the gravitational force added to the drag force. Again, these forces are then used to find the ball velocity and the ball position. To find drag, I had to experiment with the code. I changed B until the final velocity of the model matched the final velocity in the Tracker video, with the final velocity equaling negative 1.457 meters per second. After much experimentation, I found B to be equal to 0.0025. Here are the computational models given by the code. Here we see the gravity model, and here the drag. Here is the raw data. It's from Tracker, gravity only, and gravity and drag. These have time in the first slot, the first column from 0 to 0.495 seconds, and then the y position for each of the models. Here's the final graph, y position versus time, with the red line being the observed, the green line being gravity only model, and the black dashed line being drag and gravity. As you can see, there are discrepancies here, with the red not equaling the black and green, but eventually they all come down into one line here. Black and green always being equal to each other. What does it mean? What the graph is showing is that the drag force is not having much effect in this particular case. Unfortunately, I believe this to be wrong. The models that should predict terminal velocity are gravity and drag, and the Tracker video. The gravity only code should not predict a terminal velocity, as it seems to in the graph. This is because you need drag force to slow down the object, meaning the gravity-only graph should be a straight line. What if? If an object was initially thrown downward, the terminal velocity would be the same as an object that was initially dropped from rest. I used the same model, altering the initial velocity to have an object that was thrown down, and I found that the objects all approached the same terminal velocity. Why? Well, it's because when the gravitational force equals the drag force, the object will reach a constant terminal velocity. Thank you very much for watching this video.